How do we survive in a world that is heating up?
We're already seeing the early warning signs.
And running out of oil.
This shortage of petroleum fuels will have an impact on everybody's life.
The most brilliant minds in the country are moving us beyond oil to cleaner fuels and technological breakthroughs. How about a car that makes its own fuel?
I got a big poof of hydrogen and steam.
A commute for pennies?
It consumes only about 50 cents worth of electricity.
Fuel from your backyard waste. Big power in tiny packages.
And we said, wow, I wonder if we could get organisms to make batteries.
In the next hour, scientific breakthroughs that will keep you moving.
What you have is a new fuel.
It's a green fuel revolution. Imagine a world where car batteries are assembled by biological organisms. They are non-toxic, biodegradable, and very powerful. Step into the world of Dr. Angela Belcher. She walked on this beach during her college years at UC Santa Barbara, on the few days when she wasn't busy getting degrees in chemistry, biochemistry, molecular biology, and electrical engineering. This is where she got her inspiration for a radical line of research that could change batteries forever.
So when we're thinking about how to make new technologies, we're going to look at it from a very new perspective. 500 million years ago, when the environment of the ocean changed, organisms that were soft body organisms didn't make hard materials, didn't make shells. But through selection pressure and through changes in the chemistry and the environment, they learned how to make materials like shells.
Only a multidisciplinary mind like Angie Belcher's would look at that and think this.
And we said, wow, if organisms could make shells, I wonder if we could get organisms to make batteries.
The idea of teaching organisms to make batteries seems out of this world. But Angie Belcher has found a way.
The reason that it's such a special structure is it's based on nanotechnology.
Nanotechnology refers to one of the smallest units of measurement, the nanometer, a billionth of a meter. Like the abalone shell, Angela Belcher wanted her nano batteries to harness the power and perfection of biological systems.
I isolated the proteins that are involved in making the really exquisite structure of the shell. And by looking at the periodic table, I started thinking, well, what about all these other elements? Can these same proteins that work for shells, can they work with other kinds of elements? And in fact, it was pretty amazing they could work on other kinds of elements. So what we had to do was pick an organism that was easy to manipulate and could be propagated on a very short time scale, so we picked viruses.
The virus, it usually makes you think disease, but in Angie Belcher's lab, it's a hard-working green machine.
And then we actually start with about 1 billion viruses that are all genetically identical to each other.
Even though the viruses are identical, they have minute differences, the same way identical twins can look and act differently. What Angie Belcher and her students need to know is which of these viruses will bond with a metal oxide material. That's what makes them conduct electricity. Out of 1 billion, only a tiny handful will succeed.
Now these are the winners. These are the ones we're going to keep and test to be able to grow our electrode materials. We take those and we isolate them.
These winners are taken for a ride down to Dr. Paula Hammond's lab. Here, they'll work 24/7.
We can build very, very thin films simply by taking one material which has positive charge along it and another material which has negative charge.
The beauty of this virus is that if you put it near a sticky surface, it begins to organize itself in rows. Like bricks and mortar, the viruses stack themselves. Pretty soon, they've built a solid plate. This is the plus side of the virus battery. On the other side, a different virus builds the negative plate. To finish off the battery, tiny wires are attached.
And this is the final product, an ultra-thin, ultra-lightweight, fully water-based virus battery. this is very exciting. Being able to build a high-capacity lithium battery allows us to not only look at green approaches to building these battery systems, but also enables us to make extremely thin films, which then provide promise for micro batteries and large-scale macro batteries, which can be rolled up, have very light weight, and be used for portable products.
This is a lithium-ion rechargeable battery. Now, there's other advantages in the fact that once we have the right sequence, we can make millions, and billions of copies of it, and every time we make it, they're exactly the same, and they'll self-assemble into the structure.
It's amazing what you can figure out when you spend a day at the beach.
If you think about how abalone makes shells, they don't use any toxic materials. And when the abalone dies, they don't add toxic materials back into their environment. To us, that's a wonderful pattern to follow.
One day, Angie Belcher will test thousands of these batteries in a hybrid car. But already, a new breed of battery is taking the plug-in hybrid to 3-digit mileage.
We go from a 25-mile-per-gallon car to a 100-mile-per-gallon plug-in hybrid. And that's an enormous reduction in the amount of consumed gasoline.
It will take car batteries far beyond their humble beginnings.
There have been 3 major types of batteries that have been used in automotive applications. The first one that we used was the lead-acid battery. That's the battery that you have in your car today. It's cheap, but it's heavy and it doesn't store a lot of energy. The second generation is the nickel metal hydride battery. That is a battery that has better energy density and better power density. However, it still doesn't have the cost you need to make a mainstream plug-in hybrid. So the new technology that a lot of development is focusing on is called the lithium-ion battery. And the lithium-ion battery is represented in the next wave of battery technologies.
There are some technologies in the lab now, especially from some companies still in stealth mode, that will use quite new chemistries or new physical forms of materials to produce better results. I think the jury's out on whether those are the breakthrough that the plug-in hybrid advocates are looking for, but there's a distinct possibility that something dramatic will happen in this space.
One of those breakthroughs is happening in the Material Sciences Lab at MIT. Dr. Yet-Ming Chang is the master of battery power. His kids sometimes wonder why their toys move so fast. But it's not all child's play. Yet-Ming Chang is developing a battery that will help a plug-in hybrid get over 150 miles to the gallon. Just think what that would do to your gas bill. Today's hybrid electric cars use nickel metal hydride batteries, but they're expensive and bulky.
You don't want to lose your trunk space, and you can't add weight to the car.
And they can wear out in just a few years. When Yet-Ming experimented with lithium-ion batteries, like the ones in laptops, he discovered why they wouldn't work in a car. They can short-circuit, heat up, and explode.
Unacceptable for the vehicle market. We started looking at a class of battery materials called olivines. Olivines are actually a class of minerals that are widely found in nature, the geological minerals.
But in the lab, he broke them down into tiny particles and added metals like aluminum and zirconium.
In experimenting with those materials, we made this discovery that we could get very high charge and discharge rate capability out of this material.
The result was a particle that would pack very tightly inside the battery, creating lots of potential for electric charge. To test his material, Yet-Ming Chang has to go to the glove box. With toxic, highly flammable chemicals, he's going to make a new generation of lithium-ion batteries.
And now I'm going to assemble the cell here, and I'll do so using a pair of tweezers. Now what I'll do is to take out this positive electrode and lay it right on there like that. And now I'll add the liquid electrolyte.
He removes the battery to test it in his lab.
This is one charge-discharge curve for a test cell like I just assembled. And what it shows is the voltage on the vertical scale. And here's 3 volts, here's 4 volts, 2 volts down here.
His battery can discharge itself in seconds, which means it can deliver power fast. That's what cars need.
This is called a 26650 cell, and it's a little bit bigger than a D cell.
But electricity runs through it like lightning. It is 10 million times more conductive than the previous lithium-ion battery.
The key thing is that it can supply enormous power.
To see that power in action, take a look at the kilocycle.
The kilocycle is roughly the same size and weight as a conventional motorcycle. It has a battery pack and an electric drive system, and it's designed for the quarter-mile drag strip race.
What you're about to see is a test of the power delivered by Yetming's latest batteries.
The 0 to 60, about 1.4 seconds. Towards the end, as it's nearing the finish line, is that you'll see this, essentially a fireball. The battery supplies so much power that it's destroyed the motor. It sent the motor up in flames.
Not great for the motor, but it's a new milestone for battery power.
For every one of those drag strip runs, the kilocycle only uses about a nickel or a dime's worth of electricity. And so even though it's a demonstration of power and not fuel efficiency, even there you start to see the benefit from fuel efficiency.
With this discovery, Yetming Chang plans to revolutionize the car industry. Already, he can get more than 150 miles per gallon in his plug-in hybrid.
A fully charged battery allows me to make the round trip to my home in Framingham and back to work the next day, and I end up using about a third the amount of gas. In terms of the dependence on foreign oil, that's an enormous reduction in the amount of consumed gasoline.
Andres and Adrian are part of a special unit. They search the streets of New York City for hidden sources of energy. Tucked away in a cellar below street level, the target is found. Pure 100% nasty New York trap grease.
Start taking them out now?
Almost everyone has heard of powering cars with diesel fuel from fryer grease or soybean oil. It's become almost trendy in recent years. But few people thought you could do anything with this garbage-filled trap grease. And no one ever imagined you could use sludge like this to power one of these.
We take gross fats, greases, oils, and turn them into jet fuel.
Jet fuel?
Well, we work with crud.
And with a process they call Sentia, even the ugliest grease can be used to fly jet planes.
Pigs really do fly.
Sentia stands for Crudus Potentia, which could mean either green energy or possibly the power of crud.
Finding a green alternative to jet fuel is critical. A coast-to-coast round-trip flight pumps 2.5 tons of CO2 into the atmosphere for every single passenger on board. That's as much carbon dioxide as you put into the air if you drive your car for 3 months. It's a major factor in global warming. But regular biodiesel is no solution. It would turn into a solid, unusable mass due to the low temperatures and pressures of high-altitude flight. Luckily, these scientists think they've found the answer. In your frying pan.
And so we have to start with the idea of we're going to make a fuel that, from the engine standpoint, is indistinguishable from the petroleum-derived jet fuel.
Okay, but just how does it get from the drain to the airplane? That's where Andres and Adrian come in.
Yeah, I go in these basements, I suck out this grease.
I go out there and I make it happen.
Yeah, Andrew, I got an emergency. Can you go to dispatch? You know, never in my wildest dream could I have imagined it with so much grease in New York City.
This urban energy exploration is the brainchild of George McDonald.
New York uses over 180 million gallons of yellow grease and about 60 million gallons of trap grease every year. When I first did the research on this, I came to look at Manhattan and the rest of New York City as if it were one giant oil well.
George McDonald's plan for trap grease is pretty slick. Through his nonprofit group, the Dough Fund, he's found a win-win equation. Former homeless people.
I'm on 88 and 2nd Avenue.
Useless trap grease.
Not only can we turn this gunk into fuel, but we can clean our air.
Today, we're getting over 3,000 gallons a week.
Converting this gunk into anything useful is a tricky chemical problem. A problem these guys have solved. Dave Butler got a Mr. Wizard chemistry set when he was 7 years old. He's been experimenting ever since. Now, with a chemical engineering degree, he's taken on his biggest challenge. Any tinkerer can make fuel out of French fry oil, but this is a little more complicated.
Joe, don't stop. Oops. You all right?
The waste oils and greases arrive to us contaminated with a variety of foreign objects. Coffee cup tops, rubber gloves, mop fiber from cleaning the floor.
Where others see unusable gunk, Dave Butler sees low-cost biodiesel.
We mechanically screen the stuff to get all the solids out of it.
In this greasy soup, there are long chains of molecules, which Dave knows he has to break down to make fuel. Others have tried it with high heat, but that takes energy. Not the way to go when you want green fuel. Dave was sure he could find a better way, with creative chemistry. Through trial and error, he's found the perfect combination of acid, methanol, potassium, and low heat. Together, these strip away the fats and glycerin which would gunk up your car.
The process starts with Ed determining how much free fatty acid is inside the oil. Depending on the amount of free fatty acids, the computer decides to inject more or less of our acids, bases, and other chemicals into the reactors to start the biodiesel cooking. After it gets into our reactors, we warm it up to about 120 degrees, and we begin to strip it down to a very clean and pure biodiesel.
He sells it to distributors for $2.23 a gallon. Meanwhile, down in North Carolina, the Sentia team has just gotten their latest batch of grease.
So we're anxious to hurry up and use that before it drives us all out of the lab.
Using it around here means turning whatever it is into jet fuel. Dr. Bill Roberts has always had an eye for unusual fuel sources.
When I was in kindergarten, I convinced my best friend, Peter Calvert, who lived on the street, that we could build a moon rocket in his basement. And we were moving along slowly but steadily until his father found out that we were trying to disassemble the gas furnace and turn it into a rocket.
Years later, he's still looking for unusual ways to get airborne. Today, he's using trap grease.
Well, ethanol's been around for a couple thousand years. Biodiesel's been around for about 30 years, but this process is brand new. This is very cutting edge.
It's a tall order. First challenge, the jet engine.
The infrastructure required for an aircraft is in the billions of dollars. And so the jet engine manufacturers are saying, we are not going to make a jet engine that will work on your fuel. You need to make a fuel that will operate with our engines. And so we start with that idea, we work backwards.
Next challenge, the flying conditions. It's cold up there.
Now these molecules don't have the properties that we want. They're often solids at room temperature, and that clearly won't work in a jet that's flying in the atmosphere at minus 50 degrees Celsius.
So how do you make a pig fly?
In our first step of our process, we break everything down to the simplest form of fat.
We take low-grade fats, animal fats, vegetable oils, used cooking oils, grease, whatever, subject that to high temperature, water, and high pressure.
The trap grease separates into free fatty acids and glycerol. Now, they're able to take the glycerol, the really thick stuff, away. And then they take out the oxygen, because oxygen is free when you're flying, so jet fuel doesn't need it.
This is a continuously stirred autoclave, which is really just a very high temperature, high pressure stirred reactor. and we're talking almost 1,000 degrees Fahrenheit, the free fatty acids we take and we heat that even further, pressurize it even more, and that breaks the molecule down and strips off these oxygen molecules, which we don't want.
We're left with a long hydrocarbon, which resembles what petroleum looks like.
So at this point, it's just like petroleum. The molecules are arranged in a straight chain like this. Trouble is, petroleum has a low flash point. Not good for airplanes. In the third step, heat, high pressure, and a catalyst force the molecules into a compact cluster. In this configuration, it is much less flammable, like the kerosene that jets use now.
Coming out of this third step process, we have a class of molecules that looks virtually indistinguishable from the petroleum-derived jet fuel that we're trying to make.
We think that by the end of the year 2008, we'll be ready to produce fuel on a commercial scale.
Bottom line, it comes from disposable grease. It adds fewer greenhouse gases to the air than regular jet fuel. And it won't negatively affect your foreign policy.
The jet engine cannot distinguish this fuel from the fuel that you would get out of the Middle East. But one question that seems to come up quite often is, can I use human fat from liposuction as a potential fuel source? And sure, we can do that. So if you'd like to volunteer, give me a call, and we'll see what we can do.
What if you had a car that made its own fuel whenever you needed it? You would never need to gas up again. Dr. Jerry Woodall found a way. Accidentally. One day he was experimenting with semiconductors in his lab, melting together two metals, aluminum and gallium.
And when I added water to this melt to clean the melt out, I got a big poof of hydrogen and steam coming out of it, and it was quite spectacular and very surprising at that time.
Jerry's poof was a very happy accident.
Well, I was very excited about it. It took me a couple of hours of pondering it in my office to figure out what was going on.
He had found a way to make hydrogen on demand. Usually, aluminum has a protective layer created when it comes in contact with oxygen.
It forms a skin of aluminum oxide on aluminum, which protects it from further corrosion or reaction with water.
But when Jerry added the gallium, it removed the aluminum's protective shield. So now the oxygen and water can react with all the aluminum, freeing the hydrogen instantly.
If you have an aluminum-gallium alloy and bring it in contact with water, the hydrogen in the water is split off from oxygen to become free hydrogen gas.
Jerry uses a little candy to explain his breakthrough.
Take, for example, this piece of candy. It's chocolate in the middle and candy on the outside. And if we were to remove the candy from the outside, it becomes pure chocolate and it's very reactive.
Just like the chocolate mess, the hydrogen is released and bubbles to the surface.
2, 1, and liftoff.
NASA has been using hydrogen fuel in its missions for decades. Trouble is, it's been very expensive to make and highly explosive.
The truth of the matter is that people don't like to have large quantities of hydrogen sitting around.
With Jerry's alloy, you don't have to worry about turning into a rocket on the highway.
We make stuff that is safe to move around and has a high energy content and can be converted into hydrogen when you need it. We'll have to develop an infrastructure that allows us to distribute the fuel to the customer who's going to use this.
You'll just buy a tank full of pellets and plug it into your car.
So this technology has a very good chance of reducing our dependency on foreign oil, and the reason for it is that we are using aluminum, and the aluminum ore is located in places other than the Middle East. It's located in the United States, in Oklahoma, for example, so we have a very good chance of reducing our dependency on foreign oil.
Unlike many other hydrogen technologies, Jerry Woodall's method does not produce carbon emissions.
There's actually some significant benefits of fuel cells and hydrogen propulsion, but the issue has always been getting that hydrogen to be affordable and making sure that it's not a Trojan horse of a lot of carbon emissions, especially if that hydrogen is made from, let's say, a lot of coal-fired electricity.
Jerry expects to be powering golf carts soon and is sure his grandchildren will drive with hydrogen.
My dream is to have 100 million cars running on our gallium aluminum alloy, in which we add the stuff that's falling on my head from the sky right now, water, the ultimate renewable energy source.
The most efficient hydrogen machine on Earth is one we see every day. Each time the sun shines on leaves, they make hydrogen. What if we could make all the hydrogen we need with solar energy? At the Massachusetts Institute of Technology, Dr. Daniel Nocera is working on it.
I started worrying about energy the day I became a scientist. How much energy we're going to need in the future, being carbon neutral. Turns out that in 1 hour, more energy hits the surface of the Earth than we use in a year. So there's a lot of energy coming out of the sun that we just aren't doing anything with.
Dr. Daniel Nocera is determined to use his skills as a scientist to capture that wasted energy. He hopes he can use sunlight to make hydrogen.
So here's our inspiration. It's this tree, and it's these leaves on the tree, because they're amazing machines. They take sunlight, the sunlight that's hitting them right now, and they're really buzzing with electricity.
Inside the leaf, the light of the sun triggers an extraordinary molecular dance, photosynthesis. During this dance, the tight bond between oxygen and hydrogen in the water molecule is broken.
Water by itself isn't a fuel, it's just too stable. But if the atoms in water change partners and form 2 molecules of hydrogen and 1 of oxygen, then we have a very highly energetic fuel.
If humans could do what the leaf does, we would have a nearly limitless supply of clean hydrogen to run our cars and power our homes.
So we need to get into the lab and do what the plant does.
Dan Nocera set out to do that 25 years ago, but decoding nature is rarely simple. After years of experiments, he and his team have come up with a special compound which he believes can split the water molecule. The compound has at its core rhodium, a precious metal from the platinum family.
We need to see if this compound works. Does it really act on water to make hydrogen and oxygen? So to do that, we actually bring the compound down into this lab, and here we have an artificial sun.
Here in the lab, sunlight is provided by a powerful, room-sized laser. The experiment begins, and everyone watches closely.
I had yellow over that. One of the first things we do is just look for, like Don Ho would say, tiny bubbles.
Bubbles would mean that with his laser and special compound, he has created hydrogen. Even though the light of the laser looks like it's steady, it will actually flash for the tiniest fraction of a second, known as a femtosecond.
So why does the laser have to be that short, this millionth of a billionth of a second? That's pretty short. Well, the reason is because once the light gets dumped into this compound and makes this highly energetic excited state, we need to follow that light around in real time. So we watch the energy flow from this excited state of this special molecule, this compound. We watch it flow in this compound and then watch it dissipate or flow out of the excited state into the water to break the bonds, the hydrogen-oxygen bonds of water, to make hydrogen and oxygen. How long was the other one acquiring for?
It happens every day in nature. Leaves convert sunlight into fuel. But to accomplish that in the lab would be a small miracle. Their computer and high-speed camera will record the slightest changes. At first, nothing happens, but after a few minutes, something moves. First one bubble, then more.
And lo and behold, what you saw is bubbles. We could see the bubbles literally coming out of the solution. Once we see that happening, we then know the system is working, and that's an exciting event. But then after we analyzed that bubble, we were able to show that indeed it was hydrogen. At that moment, we knew we were onto something.
It is a major achievement, but hurdles remain. In this experiment, Dan Nocera did not split a water molecule, which is what the leaf does. Instead, he used hydrochloric acid, which contains one hydrogen and one chlorine molecule. That bond is easier to break than the bond in the water molecule. Also, the rhodium in the special compound is far too expensive for commercial use.
So there's no way you can run a large-scale economy based on rhodium.
But the experiment brings Dan one step closer to making hydrogen.
It's given us the insight to figure out what we need to do now to use cheaper metals, things like iron or nickel, to split water to hydrogen and oxygen. If that is accomplished, we have a new energy ballgame for the world.
In the new ballgame, there is no longer any need for oil.
Because now oil is equivalent to water plus light. So that's the hope. That's why the sun is so interesting to people who are looking for the nirvana, the ultimate answer to the energy problem. In the meantime, it's going to be really important to use lots of technologies to fill in while we try to catch up with nature and do photosynthesis.
What if you could find the solution to the fuel problem right in your own backyard? Dr. Lonnie Ingram thinks you can.
We work on processes to convert this yard trash and shredded wood into automotive fuel.
His secret? A radical new way of making ethanol, cellulosic ethanol. In recent years, ethanol has been billed as the great green hope to replace petroleum. People all over the world are growing their fuel. In the U.S., it's usually made from the kernels of feed corn.
Today, corn is being used to produce about 5 billion gallons a year.
But many scientists are saying, beware of ethanol.
Basically, you don't want to need so much biofuel that you would end up competing with food crops.
In Mexico, tortilla protests have filled the streets as corn, a basic staple, skyrockets out of reach.
Are we creating a situation where people are enjoying a luxury of travel at the expense of people who just need a basic diet?
Lonnie Ingram looked at the ethanol problem and he wondered, could he make ethanol out of the non-edible parts of plants?
Corn cobs and the corn stems and leaves could be used to make ethanol.
He was inspired by the way things grow out of control in Florida. Lawn clippings, orange rinds, and sugarcane stalks. Floridians are practically swimming in the stuff.
These are piles of wood waste, yard waste from Gainesville, Florida.
In the whole U.S., 1 billion tons of woody biomass are produced every year. But figuring out how to make ethanol from all these leftovers wasn't so easy. Lonnie Ingram knows his history. He knew that woody biomass had been used as a fuel source before.
In the First and Second World War, portions of wood were being converted into fuel.
Alcohol was made from sawdust, but that process was very inefficient. It could never be an important green fuel.
Back as early as the 1900s, there were experiments being done to produce sugar by cooking woody materials in dilute acids.
Lonnie started out the same way. He chopped up the stalks and stems into a uniform small size.
Once the size has been reduced to less than an inch or so, the material will be treated with dilute acid at elevated temperature to solubilize a portion of the sugars and to open up the structure of wood.
But after that, he knew he had to travel a different road, a road that was green and efficient.
In the conversion of woody biomass into ethanol, there was a problem, and that problem was with the many different types of sugars that are present.
Corn kernels, for instance, contain one easy-to-digest sugar, but stalks and stems contain several different kinds, and those sugars are tougher to break down. But tougher doesn't mean it's impossible. After much trial and error, Lonnie Ingram found the secret.
We started with E. coli, an organism which is present and an integral part of our digestive process.
Left alone, the E. coli turns cellulose into a worthless lactic acid. But Lonnie Ingram saw a way to tweak nature. He added 2 genes to the E. coli bacteria and transformed it into an efficient fuel-making machine.
This is the organism we developed. This same organism can use those sugars and convert those into ethanol. These thick colonies of E. coli on this plate are fermenting as we speak.
Now, a genetically enhanced version of the organism that digests our food turns stalks and leaves into a valuable fuel.
Each dry ton of this material can be converted into 50 to 100 gallons of ethanol.
This could actually end up roughly tripling net farm and ranch income and give us in America about 750,000 new jobs building that new biofuels industry.
Woody biomass could replace 35% of our automotive fuel in the future without hurting our food supply. A new plant in Jennings, Louisiana is already online and can make up to 30 million gallons of ethanol every year. More facilities are on the way.
This can help. This can make a large contribution.
In the future, it will be one of the choices at the gas pump.
So you drive up to the fuel pump with a credit card and a calculator to figure out which blend will give you the cheapest driving that day.
But what if you could drive around without ever going to the gas station? That's Bob Schneebus's way. Bob's just the kind of genius who may break our addiction to oil.
If we're ever going to get out of the problems we're in on this planet, you know, of our transportation and conspicuous consumption and, you know, all that stuff, we're going to have to do it with electric vehicles.
Bob's mission in life is to show people that green can be easy and fun, like his homemade electric scooter.
I wanted something so darn simple and straightforward that, you know, it's just kind of like a punch in the mouth. Something you can really understand and you get the meaning of it. A couple batteries, 2 motors, you know, a steering.
All his inventions run on clean, renewable energy, including his solar big wheel. The solar panels above his garage charge his batteries, which he then uses to power his vehicles, even the ones with 2 legs.
I had some knee surgery and stuff, and working out at the med school, I just wanted to know what's the motion involved in walking. And once I get a curiosity like that, I usually can't help myself. So the only way to find out is build a working model. So I basically built myself down the legs. They're all my size, all the proportions and everything. That's me. And this is a solar powered vehicle. I charge it off the sun. Normally I got solar panels up over top.
And why does his solar walker look like Arnold Schwarzenegger?
Well, we got a governor now who gets it. He really gets it on the environmental issue. And if I can do anything to help Arnie get on some sustainability issues and transportation issues, things like that, I'll do whatever I can to help him. So he's going to have, you know, a suit jacket, a white shirt, a tie. It'll probably end about here. That's where this is going out. It's a work in progress.
The Solar Terminator runs on 100% renewable fuel, but it's a limited edition. If you want one, you'll have to talk to Bob Schneebus. While the rest of the world looks for the best green fuel, physicist Amory Lovin says the biggest part of the fuel problem has been sitting in your garage all along.
The more I thought about the physics of the car, the more obvious it became that people were thinking about it backwards.
Today's cars are big, fast, and powerful. But when it comes to fuel, there's something wrong with the math.
As a physicist, I've been wondering why our cars use about 1/3% of their fuel energy to move the driver.
Turns out, nearly 90% of all your fuel never makes it to your wheels. where does all the fuel go?
It's lost in the engine, idling, drivetrain, and accessories.
Subtract all that, and you're left with 6% of the original fuel, which accelerates the car and heats the brakes in the end.
Only 0.3% of the car's fuel energy actually ends up moving the driver.
Amory Lovins and his green fuel team at the Rocky Mountain Institute went to work.
There's so much waste out there today that we do feel smarter design and technologies can radically reduce that waste.
They wanted to invent a new, super efficient car, but they didn't want to make it too small.
If you do that, the vehicles actually become less safe, and they also become less desirable for, let's say, American consumers that have large families.
So how do you cut waste without cutting size?
I started thinking about that whole new design space of combining ultralight, ultra-low drag with hybrid. That turned into the hypercar concept.
They looked at every part of the car with fresh eyes.
Big factor is the air conditioning unit. In fact, in some cars, the air conditioning unit is sized to be able to cool an Atlanta house in the summer.
Like a green home, their car would have insulation and double-paned windows.
Part of the issue with these efficient vehicles is they have to be designed to maximize integration.
Car parts like seats would be integrated into the car chassis.
And also provide a wraparound feel for luxury without having to be thick.
If we can actually make the car lighter, we require a smaller powertrain. We require a smaller engine. We require fewer batteries.
But their biggest fuel savings came, ironically, from the race car industry. Carbon fiber.
Carbon fiber has 10 times the strength of steel.
It weighs half as much, but
carbon fiber laid up by hand the way you make race cars is expensive.
To use carbon fiber in a consumer car, Amory and his gang would have to find a new way to make it. Easy. They reinvented the technology.
Just listen to the sound. Plastics have changed since that 60s film, The Graduate.
Never before has carbon fiber been made so strong, so quickly. At Fiber Forge, 50,000 strands of fibers are woven into tapes. Tapes become flexible panels. Panels are heated together.
This one's about 20 layers thick.
Car manufacturing at blazing speed.
So this step is 3 minutes, this step is 3 minutes, and then the final forming is 3 minutes. So ultimately, you can make 50,000 or 100,000 units a year with this process, whereas it's really going to be the highest volume composites process in the world.
Today's car frames require hundreds of parts, which add weight and fuel cost. The hypercar frame is made of 14 parts, which snap together.
And this structure makes it immensely stiff and strong, and yet very light.
There is a widespread perception that lighter vehicles are less safe. That perception, we feel, is wrong. The lighter weight car is going to accelerate better, is going to handle better, and is going to brake shorter than a heavier car.
They cut even more fuel losses by tucking in the side mirrors, making the tires out of a stiffer material. That minimizes flexing, which eats fuel. They even cut weight in the headlights. The result?
The next generation hypercar, a vehicle that is lightweight and has plug-in hybrid capability that we think will get to market in 3 to 5 years.
It will handle 5 adults in comfort. It'll haul a half ton up a 44% slope. Very brisk acceleration, 0 to 60 in about 7 or 8 seconds.
It's an SUV that will get more than 100 miles per gallon. Now, car makers are calling Amory Lovins.
You say, well, we wanted to make this car in the first place. Now we see a way to do it. Let's get together.
The hypercar puts fuel hogs to shame. In fact, it's so efficient, it doubles as a rolling power station.
Your car is going to be sitting there with potentially a considerable amount of stored energy. And at that time, it might be more efficient to take that energy and provide it back into the grid. So it goes 2 ways. We call that vehicle to grid, and the plug-in hybrid essentially enables you to feed this electricity not just into the car, but out of the car at peak times.
How does that work? Well, your fuel-efficient car would have energy to spare. Each day, you sell your extra energy back to the power company. And at the end of the month, you get a check. Imagine that. The car, one of the biggest fuel problems, becomes the energy solution.
If you do a quick thought experiment, the actual amount of power that all the cars on the road generate is actually 7 times the power of all the electricity power plants in the US combined. So our cars represent a much larger power source actually than the electricity grid. It shows the revolutionary potential of these new cars to provide energy in ways we've never thought of before.
A road with cars that redefine efficiency and innovation.
We're going to be using radically less energy.
A gas station with a limitless variety of fuels.
We're going to need it all. It's going to have to be an energy mix.
A world chock full of bright green choices.
There's an energy in the science community that we finally are getting enough of these tools.
With brilliant minds focused on the future, overcoming our addiction to oil is possible.
We're changing the world.
接下来，他们的任务搞破坏，他们的专长大爆破，非比寻常的爆破科技，超震撼完美演出，爆破分子接着播出。